The starting point of the classical mechanics would be to first of all, start with the generalized coordinates. That's how the topic starts with. Usually, why do you want to have this, and what is the transition? First point I want to explain first of all, when compared to the BSc level mechanics, in the classical mechanics, what is the major difference? So that should be clear to you. So whatever mechanics that you are actually learning in the BSc level will be called by the name Newtonian mechanics. Of course, everything is Newtonian, but however, we give some names so that you know whether you are distinguishing between the undergraduate mechanics or the postgraduate level. So for that reason, it is traditional that people call by the name Newtonian mechanics for whatever you studied until your undergraduate course. The objective of the classical mechanics is to understand why there should be an equation looking like F equal to ma. That is a question. Now, what is the answer to the question is, the answer is this. The answer is discovered by Hamilton. And Hamilton has given a statement. Now, that statement is what is known as the Hamilton's principle. And Hamilton says that, okay, according to this principle, everything in the nature obeys. That is a statement. And that everything happens to be F equal to ma in the case of mechanics. So Hamilton principle is a little more wider. It has a wider applicability than mechanics. Okay, and to understand this better, a kind of understanding is, this is equivalent to, so I'll put 3 lines here. This is something equivalent to a principle that is already known to you. Generally in optics, I think you must have studied in optics this principle, what is known as Fermat's principle. It's going to be very similar to that. So there is no big difference. Whatever Hamilton is going to tell in mechanics is what exactly is the statement in the case of optics. So small change is there in mechanics to optics. So that small change, because of that small change, the name of the principle is also simply changed. Well, this is called Hamilton's, and that is called Fermat's. If you are going to start the light source like a torch light, for example, or a laser beam, if you switch on, then the light travels in straight line and reaches to another point, as long as you don't have some medium inside. If you are going to have some different material medium like glass, plastic, and then some other transparent material, then followed by air, like that, if different materials are coming in between, then there will be bending of the ray. But if nothing is there means we are talking about vacuum. If nothing is there, then once you start the light, that is called as light source is switching on, then the light will travel in a particular straight line and then reaches to the point B. And because of this reason, the optics we usually called the ray optics. That's how you learn, first of all. So ray is actually a straight line. So once again, you ask the question, what is the question is, why light should travel in straight line? Light can travel like this and come. Like this it can travel and come, right? So why light did not go like that? And the answer is Fermat's principle. And Fermat principle says that light will travel in that particular path for which the time becomes minimum. That is, time required to travel from one point to another point has to be a minimum. So you got the point now. The point is that the question is why light has to travel in straight line but not in either. The answer is there is some principle called minimization of time, and that principle is called the Fermat principle, and nature obeys this principle. That is the idea. And once this is clear to you, now we are ready to go back. Light is traveling in straight line. That is what is visible. But why light is traveling in straight line, that is not visible to you. So that is the point which is coming as a principle. The principle is not directly visible to you. This has to be understood mathematically. Remember, once again, F equal to ma is written as a consequence of doing the experiment. Therefore, it is based on the experimental evidence. F equal to ma, where from it came? How Newton knows that equation is, it came from experimental evidence. He has done experiment and lot of data is there, and all that data is compressed into one equation. So even though Newton is doing experiment, being a physicist, he is the person who is inventing the concept of differentiation. So the idea of the derivative itself has come from the Newton. Remember that. So there are many formulas are there. Newton's differentiation formula, Newton's integration formula, okay, Newton's Grigori formula. Many formulas are there in mathematics with the name Newton. So remember that he, because of that calculus idea only, he is able to write the experimental data into F equal to ma. Otherwise, this equation will not come. People have to keep, or we have to keep only the numbers. That's all. Several pages of numbers will be there. Okay, how to rewrite this entire set of data, that is numbers, in a particular equation, that has come only from the concept of the derivative, which he himself discovered sometime in 1600. Okay, 1600 is easy to remember. Exact years we will not worry about. So we are moving from the physical aspects of mechanics to the mathematical aspect of mechanics. This is very important. So to get the answer to this question, we cannot do any experiment. So the answer lies in mathematics, not in physics. Therefore, now this word is important, mathematical. So classical mechanics, what is classical mechanics is? Classical mechanics is understanding mechanics using mathematics. This is a very crucial concept that should be clear to you, that essentially whatever we are going to study in this particular semester on the classical mechanics is nothing but mathematics. Okay, so that point should be clear. Okay, once again, you should not think that, okay, some experiment is there, some pendulum is oscillating. We are not asking about any experiment. No, nothing will be there in classical mechanics. So it's all about understanding their nature using the language of mathematics. So the Hamilton's principle is going to be very similar to the Fermat's principle. Okay, Fermat's principle I already explained, okay, with respect to the time. So in the case of the Hamilton's principle is that instead of time, it is something slightly different. So I'll now write down that in the case of the Hamilton's principle, the minimization word is there in the Fermat principle also. You're going to minimize the time taken. So time is the minimized. So instead of time, something else is minimized in the case of the Hamilton's principle. Now what is that something is? That is called action. So it is just given a name, that's all. No need to worry about the terminology. So it is not time now. Time is not minimized. Distance is not minimized. It is neither time nor distance. So it is something different. So therefore, we have to give some name for that. Okay, so that's all about it. And people have given the name action. Action is minimized. Maximization. Either this or that will go on. It can be minimum. It can be maximum, depending on case by case. In one case, it may be minimum. In another case, it may be maximum. Extremization means either minimization or maximization depending on a particular system. Case by case. We can't say that everything will go on minimum, everything will go maximum. No. Okay, it's all about nature. Everywhere it works. And therefore, the principle is known as the extremization principle. So in the case of for the case of the Hamilton's principle, this action is given by this integral, the Lagrangian multiplied by the dt. That's all. So now you can understand what is happening here. In the case of it comes to the money, or it comes to the minimization of the petrol, we use the word money, we use the word petrol. So these are the English words that we use to find. And in the case of the Fermat's principle, you say time. Time is minimized. You say that looks very simple. You simply write down time. But in mechanics, what happens is, it is not a simple quantity that is getting minimized. If it is very simple, we can write down space, time, something like that we can write. Energy, for example. It is not that simple quantity. It is a quantity that has to be evaluated according to this rule. You evaluate this quantity, integral of Lagrangian multiplied by dt. You evaluate, okay, whatever it is, you call it by a. So whatever comes as an answer, that you give the name a. That a is known as action. Now this action has to be minimized. The question is this one: why nature obeys F equal to ma? Why nature should obey an equation of the form? It need not be F equal to ma. Whatever it is, that's the meaning. Whatever be the equation that is currently obeyed according to the Newton, why nature has to obey according to that? That is the question. The answer is that because nature is behaving in such a way that certain minimization or maximization always takes place. Because of that reason, this equation F equal to ma emerges out. That's what is the answer. So this kind of statement that I have written down, or whatever I said now, is the statement what is known as Hamilton's principle. So instead of saying a simple mechanical system, we will use the word dynamical system, which means that no way we are talking about any kind of static situation. That is the meaning. We are excluding all statics. So this will be the tabular column that you will be filling. in an experiment, that is what you do. At various times, you measure the position and then make the tabular column. Dx by dt is denoted by x dot. So that standard notation you may be knowing already. Even otherwise, you can now make sure that this is what we are going to use. So this is the single dot and double dot notation we will be using. So this is the, we say, velocity and acceleration. So based on this notation, so here what you understand from this experiment is that with respect to time, I measure the position. After that, I can calculate the x dot. So in this case, what will happen? You have to think. In this case, what happens is you cannot write down a tabular column like this. It's not possible. You can try. With respect to the various time, what happens is writing down the different position is not easy. Because this is making an angular, right? You don't have a position. You can't measure x-axis. What is the value? Because it is moving like this, actually what you have to measure is, you have to measure the angle. At time t equal to 0, so this is the time t equal to 0. At time t equal to 0, my theta dot is 0 and theta is not equal to 0. Do you agree for this? This is how you start the experiment. If you have done the simple pendulum experiment, you remember how you do. You pull the bob and hold it. You have to hold it. Holding means what? Theta dot is 0. That means it is not moving. And when you are holding, angle is not 0 degree. Maybe it is 10 degree, 8 degree, 11 degree, whatever it is. Some number is there. And your stop clock will show 0. The bob is not moving, therefore 0. And it is at an angle 10 degrees, therefore that is not 0. So how many numbers do you have? Or what is the data that you have? I have t comma theta dot in a simple pendulum experiment. In the case of the previous experiment, where you see that a particular ball is allowed to roll, you can allow to roll on a horizontal plane, inclined plane, anything is okay. But ultimately, what is the data that you have? The data that I'll be having is time can be there. Either you can have x and x dot, or you can measure all the x and calculate x dot. Any experiment you take, you can always find out time, position, and position time derivative. Position time derivative is called velocity. So whether it is linear velocity x dot or angular velocity theta dot, that's not a problem. But there is some position and there is some velocity. That is the point that you should remember. So there are three variables are coming. Remember that there are three variables are coming. So you're going to have three quantities. Okay, you're going to have three quantities. One of the quantities is time. T I will write down. T. That is common, so it is not changing. So therefore I'll write down. Second quantity, in first case it is x, second case it is theta. X and theta are not same because x can be in meters, right? You can measure meter, centimeter, but theta cannot be measured in centimeter. So typically it means that something is different. You can't say always distance. Okay, using the word distance is not at all correct for theta. So this gives you an indication that sometimes position may come, sometimes angle may come, sometimes it may be different, we do not know. So therefore what happens is people have an idea that why shall we write x here or shall we write theta? People thought that okay, let us not write both of them. We will write a general symbol q. You understand what is it q? Q is a general symbol. General symbol means q is nothing but position in that experiment. Q is nothing but theta in the simple pendulum experiment. And q can be something else in another experiment. That is an idea. So q, what is meant by q here is, q is called generalized coordinate. Generalized means we don't say that it has the dimension of meter. We don't say that it has dimension of radians. We don't say anything. We do not know what it can be anything. That is called general. So it is generalized. And if that is the situation, then what will happen to the theta dot? So here theta dot is there and here you have an x dot. So what shall I write here? So that should be the time derivative of the position. So therefore it becomes q dot. So if q represents the position, q dot represents the velocity. We don't use the word angular velocity. We don't use the word linear velocity. But instead we say that it is generalized velocity. When I do not know what kind of physical system I am explaining, I also do not know whether it is linear or angular, and therefore it is better to say generalized. And that is the reason why we have this kind of coordinates. And this is what is known as generalized coordinates. I'll say this is generalized coordinates and generalized velocity. So you have this, of course, for time, there is no confusion. There is nothing like generalized time. That is not there. Time is time only. So in any of the experiment, therefore, the problem comes only for the position and the velocities. And remember that that is how it looks like. And if you go back, let us go to the beginning of today's class. You remember what did I write? Here it is there. So I told you that the starting point for the classical mechanics would be understanding the generalized coordinates and generalized velocity, and then we can think about. Okay, a mathematician will say, okay, x comma y comma is a three variables, t comma q dot three variable. It's a function of three variable. So I'll say that it's a function of three variables. So mathematicians, you can easily write down. Now tell me an example of a function of three variables. Means I can easily tell, okay, xy plus something like yz square plus xyz. Anything you can write. Now that function which I have written is an example of function of three variables. So any function can be written down which can be a function of three variables, mathematically speaking. And now coming to the case of the classical mechanics, we are going to write down a function of three variables, where the first variable we are going to call it by the name q, second variable q dot, and the third variable t. This t q dot q, okay, that order is only interchange, and it is traditional to write in this order. And instead of saying that it is a function of f, we can say f of, we can say g of x, f of x, anything can be written. And in the case of the physics, what happens is we are interested in a function which is called the Lagrangian, and therefore we say it is L. It can be f only, f of q comma q dot comma t, fine. There is nothing wrong in that. It is a function of three variables. But actually that function is called by the name Lagrangian, and therefore instead of using f comma, instead of using g, we are using L. And this is a similar function. You can write any function here, which is a function of q comma q dot comma t, and this is what we are going to call by the name Lagrangian. And now you understand that if this is the Lagrangian, then we can now evaluate that if you have a function like this, you know how to integrate. If I give you a function and say that, okay, this is the function that you are having, f of x comma y comma z, evaluate with respect to dz, means you can evaluate, you know how to do the integration. And similarly, okay, if that is the situation, similarly you can perform the integral of q comma q dot comma t, that's a dot here, comma t, and then you perform with respect to the dt, and then of course this is from time 1 to time 2. Can you evaluate this? Means yes, we can evaluate. What is wrong? If a function is given to you, you can evaluate. And if you evaluate and simplify, whether you're going to simplify or not, that is a different story. If you simplify, we will call it by the name a. Even if you don't simplify, it's okay. Keep it in the form of integral. We will call that as the action. So now you understand that this is the action. Action integral. That's all. So this action integral is what is getting minimized. Okay, so and that is called the Hamilton's principle. So that's all about it. And so in today's class, you basically understood how you are going to make a transition from the undergraduate Newtonian mechanics to the graduate level classical mechanics, and the starting point would be the Hamilton's principle. That is the starting point. Or ultimately, what is going to happen is this is what is going to happen. I'll write down that. So the Hamilton's principle is going to generate F equal to me. Hamilton's principle is the underlying principle. That means this has to generate that. That is the meaning. That the meaning is Hamilton's principle is going to be much wider principle, not limited to mechanics alone. But if you say F equal to ma, F equal to ma is very particular to a physical system in mechanics only. This is not applicable to some other topic. That's the meaning. Therefore, Hamilton's principle is much general principle rather than limited to a particular topic. So that is the overall conclusion. So remember that this is a very important and crucial one. Why people, or why should I write the Lagrangian to be a function of 3 variable? That 3 variable actually comes from the experimental knowledge. Okay, any given physical system, you will be having the data for time, position, and velocity. That is the reason. Okay, with that we will stop.